Okay. Excellent. And whenever you're ready, thanks so much for being here again. And yeah, we are looking forward to your talk.
Sure. So it's a pleasure to, yeah, what did I say? Like, be here, to meet virtually somewhere. I do recognize the building, by the way, so I was there last summer, and I do recognize it. Just see outside the window, recognize some parts of the building. And I'll be there again somewhere in July, I think, each for a couple of days. And now I will talk a little bit about some recent developments. So my background is experimental psychology. Experimental psychologist. Most of the things that I do are just to do research. And maybe sort of after my PhD, I was sort of confronted with the idea that, well, there's actually a lot of room for improvement in the way that I work. And if you ask me very basic things about how to do good research, then very often, well, I would sort of know what we do, but I wouldn't really know why we do things. And I think this is typical for our field. So a lot of psychologists are now self-reflecting, thinking, how can we improve? And there's a lot of yeah, sort of initiatives and ways in which people are trying to improve. And I'll talk a little bit about these things. So how we have been moving slowly towards what you would call more transparent and more reliable science. And I'll also talk a little bit about the problems, but I always get a little bit interested when talking about the problems in the field. I'm interested in how we can move forward and improve things. So I'll talk a little bit about that. So can you see the slides actually?
Yes.
Did they just update? Yeah. All right. So you see the next slide? Just checking. Yeah. So this is a quote by Bacon, right? You see this?
We see the title slide.
Title slide. All right. Let's see. How should I? Should of course have thought of this. Share some of this. Let me try it. So that you can see the correct slides. Try it.
Yes, looks good. Yes.
Is this the next one?
We still see the title slide. But it's a full screen now.
It's interesting why you don't see the next slide. Sorry for this. Well, this is the first time I'm trying. I'll also show you the slides. Any good suggestions?
Can you go back to just opening PowerPoint? And then, no, yeah, we now see the second slide. If you can just continue on the sidebar, then I think it works out fine without having the full screen view.
Yeah, so you see just a slide like this. Shall we do that?
Looks good.
Let's just do it. Yeah, so this is okay. So then I wanted to show you this very old this. Yeah, you see this still? Yeah?
Yes.
All right, good. So this is a quote by Bacon from 1620, right? So this is a long time ago. And in this quote, he says something about the introduction, about one of the first books where he writes about Bacon. Bacon is one of the people who, if you remember from your history of science class, he was one of the people who said books should follow science. Science should not follow books, with which he responded to, for example, the church. Right? So it shouldn't be the case that the Bible dictates what we think. It should be the case that we think what science tells us. But this is in this introduction to this book he wrote in 1620, where it says, "Lastly, I would address one general admonition to all. that they consider what are the true ends of knowledge, and that they seek it not either for pleasure of the mind. So you should be doing science not because it's pleasurable for the mind. It might be, right? We have a nice job where we can challenge ourselves, but that should not be the goal. And that they seek it not or for contention, or for superiority to others, which is also an interesting one. Right? So superiority to others basically means that you shouldn't do it to feel better than other people. Or for profit, so you shouldn't do this to make money, or fame, or power, or any of these informal things, but for the benefit and use of life, and that they perfectly govern it in charity. So this is the idea that you should become scientists mainly because it should be good for other people. And this is you, right? This is
Sorry,
your motivation.
can I interrupt quickly? Could you maybe move a bit closer to the microphone, or there's a lot of static noise there?
Is this better? Can you hear it? Yeah?
Yeah, a bit better.
Bit better, but still not good?
Not perfect.
Wait, let me see which microphone. I mean, we did prepare. Just want to say that.
Yeah.
All right, I know what I need to select a better microphone.
All right, is this working better?
Much better.
Because I have a pretty good microphone here. So, all right, all right. So you were just all thinking, oh my God, I have to listen to this for another 45 minutes or an hour. Okay, so let me just repeat what I just said then, okay, so that you can hear it a little bit better. So this is Bacon telling us why we should do science. And he's saying a lot of things why we should not do science. So not because it's pleasurable for the mind, or because you get famous, or you get power, or you'll get rich doing it, but you should do it because it's good for the world and for other people. And now maybe this is exactly you, right? But there are also these concerns that some people do this for other reasons, which are not so noble, so to say. And one example of this is actually not even so very long later that people already are starting to criticize people's motivation for doing good and honest science. And this is a nice quote by Charles Babbage. This is 1830, right? So we're starting to already criticize science almost before it was a thing. People were already criticizing it. And this is a book, it's called Reflections on the Decline of Science in England. The Decline of Science in England. So it's already going downhill from this very early moment on. Some people are already complaining, and some of its causes. And here he's discussing a practice, and let me just, check in with you if you can recognize this. I know that we're almost 200 years later, but maybe you still recognize this. So he's talking of a specific practice which he calls of cooking. He's not talking about kitchen things, but cooking. This is an art of various forms, the object of which is to give to ordinary observations the appearance and character of those of the highest degree of accuracy. One of its numerous processes is to make multitudes of observations, and out of these to select those only which agree or very nearly agree. If 100 observations are made, the cook must be very unlucky if he cannot pick out 15 or 20 which will do up for serving. So this is an idea that people, if they do science, they're not objectively reporting what they find. What they're actually doing is, they're picking out the things that are most likely to support what they want to find support for. In other ways, this is what we nowadays sometimes call p-hacking. The process where you test something and you try it in a different way and in a different way so that it looks good, so you can sort of serve it up for cooking, right? So that you find, in this case, a significant result. So he's already worried about these practices almost 200 years ago. And if anything, in recent years, we're sort of rediscovering this and more broadly sharing the importance of this. So let me tell you a little bit about my specific field. And why in our field we are now thinking of this a little bit more. And I think that one of the reasons for this is that there was research that was published in 2011, and I'm not sure if you've heard about this, but if you have, just maybe raise your hand or something. But has anybody heard of research by Daryl Bem about precognition? Have you heard about this? No?
Yes, some of us have.
Some of us have, okay. So this is a set of 9 studies that were published in one of the flagship journals in the field of social and personality psychology. and a set of 9 studies where Daryl Bem showed that if you let people randomly guess about what will happen in the future, so for example, there's a very simple task where people see 2 curtains, one on the left and one on the right, and they have to predict behind which of these 2 curtains is a positive or a negative stimulus, or a picture that you can see. So people don't really know anything, and actually even more, the computer doesn't even know where the picture will appear, because these are pretty well done studies in the sense that even the computer doesn't know yet where the picture will appear. So the random number generator decides this later on. People do this task, they press a button, then the computer decides where the picture will appear, and people actually see the picture appear. So, and then Daryl Bem calculates how often are people correct. Now they should obviously be correct only 50% of the time, because they don't really can predict the future, right? So it should be 50%. But in this line of 9 studies, he basically repeatedly shows that people can do better than guessing average. So there are significant results in all these studies, which is surprising. Now let's take a look at one of them. So this example, this result in discussion, is an example of the first study in this paper. So let's just take a look at it, right? So this is the results in discussion section. He says across all 100 sessions, so people did this sort of guessing task 100 times, participants correctly identified the future position of the erotic pictures significantly more frequently than the 50% hit rate expected by chance, namely 53.1% of the time. There's a test statistic, a p-value of 0.1, 0.01. And you might be, interesting, so people can predict the future, it's pretty good. But let's read on. So he says, in contrast, their hit rate on the non-erotic pictures did not differ significantly from chance. So it's 49.8%, the p-value is not smaller than 0.05. Then he says, the interesting thing, I think, this was true across all types of non-erotic pictures. Neutral, negative, positive, and romantic, but non-erotic. I'm not really sure when a picture is romantic but non-erotic and when it is erotic, but apparently there's some sort of threshold there which we can objectively establish. Now, if you think about when it would be most useful to predict the future, and I mean, don't get me wrong, I'm pretty sure that it can be useful to predict where erotic things will happen in the future. I can see some sort of usefulness of this. But from these other categories, would there be another category where you're like, well, if I would expect an effect without knowing anything about precognition, I might expect it for this type of picture. Do you have any preference? So neutral, negative, positive, romantic, but non-erotic? You have any ideas? Anybody wants to take a guess? Maybe the negative ones? Would that make sense? I mean, I'm not sure. Just thinking that if I would be able to predict where negative things happen in the future, that might make sense, right? So I think the main point here is that it's actually not really clear why he would predict a specific effect for the erotic pictures and not for the other ones. And then if we think back about this earlier slide about cooking, where people can selectively report one of the results that they are interested in, well, maybe that's what's going on here. And actually, if we take a look at all the studies that are reported in this line of research, and you take a look at their significance, then if you look at this slide, so this is a meta-analysis also published by Daryl Bem and some colleagues. And if you look at the significance of these findings, so here every row is actually a specific effect. And then on the right, you see something that's sort of called a forest plot. The line is a null effect. All the dots are the effect sizes that are observed. And then the confidence interval around it shows whether the effect is significant or not, depending on whether there's overlap with this null line or not. So if the confidence interval doesn't include 0, then you can consider the effect to be significant. There are 2 or 3 where it sort of overlaps, but actually if you have a one-sided test, which was reported, then even these are significant. But here, this pattern is kind of peculiar. All these studies are just on the brink of this line of where things are supposed to be if they have to be significant. And this doesn't look really like a normal meta-analysis. There should be way more variation. Many more studies should be non-significant. Some should be way more significant. But the fact that they're all just barely on the right side of significance should make you sort of worry about whether this cooking process went on. Now, you might not do this kind of thing, right? You might say, well, no, I don't think this is very a moral thing to do. And if you look at research about how scientists actually operate, so this is an example by Anderson and colleagues from 2007, where they ask people, how much do you subscribe to norms, good normative behavior in science? So this is things like, well, you should be transparent and share what you've done, and you should not be biased, those kind of norms. Then you see on the left, you see bars for subscription. And this is for the black bars for people in mid-career, the other bars for early career researchers, but that doesn't really matter. So how much do you subscribe to these norms? How much do you think that researchers should be unbiased, for example? It scores pretty high. If you then look at the bars next to it, people's own behavior, that's asking how much do you actually behave in line with these norms? Then people say, well, I have to be honest, not as much as I adhere to these norms. So I don't meet exactly the highest standards of this normative behavior. But then the most interesting thing actually happens on this bars to the side. How much, if you ask people, how much do other people's behaviors live up to these norms? Then they say, well, that's even worse. So I might not be perfect, but actually my colleagues are even doing a worse job. So, you know, relatively speaking, I'm doing kind of fine. So this is interesting, right? If we ask people, how are we doing? Then we realize we're not living up to the best norms that are available. Other people are doing an even worse job. And this is something that we might want to think about, how we can prevent this. It is easy to sort of get used to current ways of working, right? If you ask people about norms, then, well, it's sort of what we're learned to do. So, for example, something that's quite normative in many fields is this is selective reporting of results that Charles Babbage, 1830, was really worried about. And if you ask people whether you actually do this, whether people do this, and there are studies, for example, Klaus Fiedler, Robert Schwartz, 2015, where they asked a bunch of people, how much do you do this type of behavior and this behavior? And then in this case, they asked, do you selectively report analysis that worked? So that means that showed a significant result or that showed an effect that you expected. And then 40% of people says, yeah, I've at least once done this in my line of research. Maybe they've done it more, but at least once they've selectively reported results that worked. Now, if you think about this, does this sound bad? I mean, isn't this sort of how scientists work? Like, isn't this what you see around you? But what I find interesting is that if you ask the general public, what do you think of this kind of behavior? Of scientists who selectively report things that worked and don't report things that didn't work. So if you ask this, then about 50% of, in this case, Americans who were sampled, thinks that researchers who selectively report what works should be fired. So this is pretty extreme difference, right? 40% of people say, yeah, sure, I've done this once. But if you ask the general public, what do you think of scientists who behave in this specific way? They say, well, I think it makes sense if these people are fired. Now, I'm not sure if these people should be fired, but I'm pretty sure that there's at least some disconnect in the norms that we find acceptable and what the general public at least expect us to do. So what's the consequence of this selective reporting? Well, one of the consequences is that it's very visible that we do this. So this is a distribution where you can see p-values reported in the scientific literature. So in some journals, people went in, they took all the p-values out that they could find for statistical tests, and then you find a pattern that you can see here. And you see sort of a curve going like this, right? You see a curve, and you would sort of expect this curve to continue on. And that's actually normal behavior for p-value distributions. If you look at the literature, depending on power, they should form a curve like this if we're examining a true effect and we at least have some statistical power. But you also see a big drop. And this is the red line on the slide. There's a big drop, and then it sort of goes down, and then it continues on. And if you look at where this big drop is, then not surprisingly, it's at 0.05. So the significance level. We report things if they're statistically significant. We also sometimes report things if they're not significant, but we definitely don't report everything. So we can just see that people selectively report things quite a lot. So this is current practice, right? This is what we see that people are doing at the moment. Now, in science, we have a name for this, and this is basically the file drawer problem, right? So we have this issue where people do not share things that are non-significant, which is extremely annoying. Because if we selectively report things that work, then we get into this problem that we get a very biased set of findings in the scientific literature. So if you take a look at this slide, this is a slide where you see a lot of dots. And all these dots are single studies. They're medical studies that examine whether things that we eat or drink, such as wine or coffee or beef or corn, whether these things are, based on the scientific literature, likely to cause cancer or actually protect against cancer, right? So there's a bunch of studies here. And of course, there's some random variation. So sometimes a study will show that it causes cancer. Sometimes it will show that it protects against cancer. But if you pull everything together and you calculate the average, for many of these things, maybe with the exception of beef, by the way, eating red meat is one of the things that might actually be not so healthy. But all these other things basically show no effect. So there's no reason to, at the moment, consider that these might cause cancer or protect against cancer. The effect is zero. However, we don't show people all these studies most of the time. Instead, what we do is we show the most extreme ones that show significant effects. So if you look at the effects of coffee, maybe we published a study that's way on the left that says, hey, coffee can actually protect against cancer. Now, all these dots close to 1, in this case, a relative risk of 1 means it has no benefit but no downside, just equal. So we don't publish these, and the ones on the other side, they might also be statistically significant, and we publish these. So we have these studies at the end, and these might end up in the literature. But this is, of course, very confusing for the general public, because they read 1 week, they read a study that says drinking coffee protects against cancer. Next week, they read a study that says drinking coffee causes cancer. And then, what are people to expect, except saying something like, well, I don't know, but science is probably just an opinion. These people are just saying different things all the time, and I don't know what to believe. Whereas if we would have access to everything that's done and there's no publication bias, we would be able to say, look, there's probably nothing going on. What you saw in the newspaper are just outliers, but there's no true effect. All right, so that's something that is a sort of a reason for concern. And I think I talked enough about sort of the problems, sort of the negative things that might happen. And sorry, I'm trying to show the next slide, which is a bit tricky for some reason. Do you see the slide with the payoff outcome?
No, we see bacon again.
Okay. All right. This trying to show it for some reason. It's having a hard time. All right, let me try to get it back.
Maybe if you go into present mode first and then share a screen.
Yeah. All right. This looks better.
We see the title slide now.
Yeah, it's weird that you don't see the next slides because I see them for some reason. I don't know why.
Otherwise, I can just pull up the PDF that you've sent around.
Let me try to... So maybe, I mean, you can see me, but I'm sort of boring anyway. So maybe I can just show you the slides. This should also work, I guess. Or maybe not. All right. Well, at least the slide is back. Let's try it like this. Yeah?
Okay. Great.
All right. So here you see sort of a payoff matrix, right? So you see two people, and this is what's known as a sort of classical social dilemma. And in these kind of social dilemmas, people have to choose whether they want to collaborate or where they want to defect. And in defect, that basically means that you don't collaborate, but you choose your own short-term interest. And this is a little bit the situation that many scientists are in. So we can do what's actually good for the greater good, for everyone. But then there's also this moment where you have to think, how would it work if I want to apply for a job? It would be kind of nice if I have this publication and then people start to selectively report and those kind of practices. So this is sort of a choice that you have to make, right? Which is very annoying when you leave it up to individuals to do the right thing when they're tempted to do something that's in their own short-term interest. So you might think, how can we actually solve these kind of issues where people have to sort of solve these dilemmas? And let's take a look at some of the things that people have been thinking about in the last couple of years of how we can actually solve this. So one of them is to generate rules. And in the case of rules, what you can think about is sort of what we've done in trying to solve social dilemmas in the field of a light bulb, basically. So when you think about a light bulb, these are very cheap, but they're not very energy efficient. But you can also have LED lights, which are much more energy efficient. And for a long time, people tried to get the general public to buy these more energy efficient lights. But people were very hesitant to do this. They were too expensive. It didn't really work. So after a while, what we did was not just leave it up to people to do the right thing, but we forced them to do the right thing. The European decided to ban the old-fashioned light bulb, and now everybody has to buy LED lights that are better for the environment. So this is one example of how we can actually improve people's behavior in these social dilemmas, which play a role in science, by generating rules. So one of the rules that people are thinking about now, or that are slowly getting instituted, are, for example, that if people publish, they also have to share their data management, or their data that underlies their publication. And if people get funded, so in this slide, this is a screenshot from the Dutch National Science Fund. If people get funded in the Netherlands, they have to submit a data management plan. How are you going to share the data that is produced with this grant that is funded? And we see that people are learning more and more of how to actually share their data. So this is a new skill for many people that they have to learn, but they were going to have to learn it because this is now slowly being piloted, that we force people to share their data, but we can expect this to become sort of a requirement in the near future, that whenever you produce data that underlies publications, you publish the research, that you'll have to share the research it's based on. Another thing that at the moment is not yet a rule is, but that's being done sometimes, is to pre-register your research. And in this case, what we ask people to do is write up, before they actually collect the data, exactly what they plan to do in their data analysis, for example. So if we have this problem that people selectively report, then one way to prevent this is to actually say, hey, take a look at what you want to do, write it down, share this in a way so that we can actually, when you publish your research, see, hey, look, this is exactly what you wanted to do. This is already common in some fields. Medicine has this, for example. And you can take a look at the consequences of this. So in this slide, you see a number of dots. Again, every dot is a single study. And then you also see a line with a small flag attached to it. And this line is at the year 2000, because in the year 2000, people were required to pre-register their primary test, the most important thing that they wanted to examine, on clinicaltrials.gov in this specific field of research. So before 2000, the year 2000, people were sort of free to analyze their data whatever, in however they wanted, or at least we couldn't see what they originally planned and what they report in the article. But after 2000, people are much more constrained and they really have to report the test that they predicted. So if you look at what happens before, then whenever you see a plus with a circle around it, that means that it's a positive result, something that supports the hypothesis. You also see a couple of sort of bluish dots that are solid, and these dots do not show an effect. And if you would count everything before the year 2000, you'd see that 17 out of 30 studies showed a predicted effect. So that's pretty good, right? Research is showing that things actually work. Then after the year 2000, Only 2 out of 25 studies show a positive effect. So the moment that people have to specify what they do and they no longer have this freedom to play around with the analysis, all of a sudden most of the things they test no longer show a significant effect. Now imagine that, I mean, this is medication, right? Research in medication. Imagine that you have to go to a doctor and the doctor says, oh, I see what kind of disease you have. Well, we have 2 pretty new drugs that can cure you. The one that was developed in 1996 and another drug that we have was developed in 2006. But both of these have been shown in empirical research to be beneficial. Then which of these 2 would you personally choose? I would guess that probably you want to take the one after the year 2000, right? Because you have some more faith in the fact that this is actually a working drug and that the statistical test was what it was. So it's becoming easier and easier to do this. Now you might say, why don't people do this all the time? Why didn't people do this 10 or 20 years ago? But then you would sort of be sidestepping an important issue. It was actually very difficult to pre-register, to make so transparent what you're set out to do. I mean, you look like a pretty young bunch of people, so you might not remember the emergence of the internet. But I still remember the first time that we actually had a computer in the house that was connected to the internet. You know, you could download something, and it was good that in those days I listened mostly to punk music. And punk songs lasted like 1 minute and 30 seconds. And you could, in like half an hour, you can just download a punk song of 1 minute and 30 seconds. But that was sort of all the internet allowed you to do. So it was pretty difficult to share information, to upload it. The cloud was not so readily developed. And actually, there's a nice story of a paper from 1960 where people are already saying, sometimes it's nice to do a one-sided test. You know, where you say, I've actually predicted the effect would be in this direction instead of a 2-sided test. But they say in this paper from 1960, yeah, but people might not believe you. They might think, oh, you only decided to do a 1-sided test after the fact. So there's flexibility. How can you convince people you did not selectively report, but you actually wanted to do a 1-sided test? And their solution is to write it in a letter, bring it to the post office, send it signed to yourself, get a stamp of the post office, and then leave the letter closed on your desk until somebody says, hey, wait, I want to see proof that you actually predicted this in advance. And then you would take out this letter. You say, look at the date stamp. It's still closed. You can open it, and that would be your proof. Well, nowadays, of course, you can do exactly this on the internet, which is a lot easier. So you can pre-register your hypothesis and share it with other people because we have opportunities to do this online. But that's pretty recent. Right? So we're starting to develop these sort of new ways to pre-register because the internet makes it possible. And this is an overview slide of the Open Science Framework, which is a platform that tries to facilitate people sharing their research, their data. It also indexes preprints. And you can see here that this is an old slide. There are now already over 10,000 registrations that people have performed on this platform. So you see that over the last couple of years, this is becoming more and more popular. And there are also about 100 journals that now offer a specific article type that's called a registered report. And this is about 100 journals have adopted this new way of publishing in the last 4 years. So that's kind of a meteoric rise. It started actually in the field of neuroscience. And Chris Chambers, who's on this slide, is one of the people who's most active in this field. And these registered reports basically ask people to write their plan. What do you want to do? How do you want to collect data? What's your hypothesis? Why do you want to do this? What are your predictions and which tests are you planning to perform? Write this all down. Submit this for publication before data is collected. And then the peer reviewers go through it. They say, yeah, this is pretty nice, but don't forget to also ask this, or don't forget to also correct for this kind of thing that can happen. And if you do all this, we will accept it for publication. So people don't have any flexibility in their data analysis. They've said what they're going to do. Of course, they're free to then explore other patterns in their data, but this is explicitly noted. So there's a certain section that's like, these are our predictions, these are the tests of our predictions, and they're free to also explore the data and report that, but in a very specific section where it's very clear that this is exploratory. But the main thing there is that even if the results don't support the hypothesis, people are guaranteed that their results will be published. So that's a big benefit of these registered reports, that people can prevent this file drawer. So this is another interesting recent development. Now, of course, you're also free to create your own new rules, right? I mean, we're talking about the norms and what people are doing, but you're also free to say, well, actually, this is what I believe in. So let me give you one example of something that I think is a nice example of how people can sort of enforce or sort of follow what they believe, basically. And this is known as the Peer Reviewers Openness Initiative. So it's called the PRO initiative. And what this initiative is that there's a bunch of people, maybe 400, 500 now, who say, I will only peer review papers that have been submitted that share data and materials, or at least explain why the data and materials could not be shared. So if you think that open science is important and it's feasible for most of the things that are published in your field, so that data can be shared, the materials that people have used can be shared so that we can transparently see what has happened, or whenever it's the case that people cannot share their data, but they can at least explicitly say, no, we have good reasons why we cannot share this data because it's sensitive, and they write it in their article. Only when this is done will people say, okay, I'm willing to accept this review request. But if people do not share their data or their materials, then, well, good luck, you can find another reviewer, but I will not spend my time on this. So this is, I think, pretty interesting. And I know that when this was proposed, when we proposed this a couple of years ago, maybe 2004, people thought this was crazy, that by default, people should be expected to share the data and materials, or if they wouldn't be able to do this, to write down in the article explicitly why not. And people were a little bit surprised that you would only review papers. They saw it sort of as boycotting certain types of submissions. But actually, if you look at what happens at scientific journals now, then many journals themselves have already said, well, we by default expect you to share data and materials, or if not, explain why. So actually the rule that a bunch of people came up with, like, okay, we will only review papers if they adhere to these basic open science principles, has now already been adopted by journals. So you can actually have sort of bottom-up change, come up with a good idea. It's not even that difficult to come up with something that's pretty reasonable and then get journals to implement this later on. So now we have rules, right? So registered reports are not rules yet, but I could see that we move to a science where people are expected to pre-register their hypothesis, which we basically see in clinical research or in medical research. But if we don't want to go to rules, then there are other things we can do to prevent sort of norm violations that we talked about, right? For example, this type of cooking. And this is a way of solving this social dilemma that I don't really like, but it's being done. So you can see this around you sometimes. And this is actually punishment. So there are now people who will punish people who violate norms. And this is an example of a researcher on this slide. His name is Brian Wansink. And he's a researcher who did a lot of research on food preferences or how people eat and food behavior, basically. He studied this. And he published a lot on studies where people would, for example, eat less in a certain type of environment or depending on some sort of manipulation. And some actually pretty well known. I used to teach some of these at least. There are studies where, for example, the size of the plate influences how much people eat. That's some of his research, where people, if they have big plates, they will put more food on their plate and they'll eat more. But there's also a study where there's a can of Pringles, and then if people eat, they will eat crisps and keep eating. But if people put a red Pringle somewhere, they will actually stop at the moment that they encounter this red Pringle. Kind of nice kind of food research. However, it also turns out that if you look carefully at what he has done, then there's actually a lot of sort of issues with this research. So this is a slide that sort of just has a screenshot of a lot of things that were highlighted where, for example, numbers that were calculated in the statistics couldn't be correct, or where text that has been written is plagiarized from other articles. And this happened in a huge amount of papers. Especially the numbers didn't add up. So if you would reanalyze the data or try to do it, there would just be something wrong. So there was just a huge amount of sort of sloppy research practices. And this has already led to numerous retractions where papers were really just so sloppy that the data couldn't confirm, like appropriate analysis of the data couldn't show the same results. Now, this is, of course, undesirable behavior, that people take a sort of shortcut and don't analyze their data carefully. The data cannot be reproduced. And then people call out this behavior when it happens. So this is an example of punishment, basically. And that's another way to solve social dilemmas, although it might not be the most desirable one, because punishment is kind of sloppy. If we punish people for what they do, then yeah, they basically suffer. It's very difficult to, well, it's not really a justice system where we say, oh, you speeded so much and then the fine is this much. No, people did something wrong and the punishment is also often quite extreme and very stressful for individuals. But yeah, it is one way that if we don't have rules and we leave it up to people and some people violate norms, then the punishment can be quite severe. So this happens if people are sloppy, but also for scientific fraud, for example. There are now people who figure out different statistical techniques that there has been scientific fraud. This is an example by Yuri Simonson, where he says that, well, people should actually share their data because it's easier to spot problems with it, but also that he can detect cases of fraud just by looking at the published statistics. Moving beyond fraud, we can also see cases where people have selectively reported. So now we have statistical techniques that if there's a field that has studied things, and basically the field consists of no true effects, but only selectively reported results, we can notice this. And one way you can notice this is by looking at the distribution of p-values. If there is no true effect in a set of studies, then the p-value distribution is uniform. Every p-value is just as likely to be observed. And if you've never heard about this, then I'll have a slide to my MOOC later where you can take a look at how this actually works. For now, if you never heard about this, just trust me that this is what p-values should look like when there's no effect and you plot all of them over hundreds of tests. P-value distribution is uniform. You can also take a look and simulate what happens if people sort of p-hack. And one way that people sometimes do this is they collect some data, they analyze the data, and if it's significant, they stop. But if it's not significant, they continue on. They collect some more data. If it's still not significant, they collect some more data and more. And they stop whenever a test shows a significant effect. If people do this, you get a p-value distribution that looks like the one in this slide. So this is called optional stopping. You analyze data until something works, and you find this kind of peculiar pattern. It's not uniform anymore. It should be uniform. But it's sort of that people have scraped a couple of the non-significant p-values to just below 0.05. And that's why you have this very weird peak that goes up, actually. So it's most likely to find a p-value that's like 0.045, then a very small p-value of 0.001, for example. So it's a very peculiar distribution, but you can recognize this if you take a look at a set of studies. One of my favorite examples here, because it's such a clear example, is the case of a paper that's published in Science, where people did a couple of studies that show that reading literary fiction improves your theory of mind. And improving theory of mind basically means you're more empathic, you're thinking about the thoughts and feelings of other people. And of course, this is what we want. We were all a little bit of nerds when we were younger. We read a little bit too many books, maybe, as scientists. And yeah, we want this to be positive, right? Reading literary fiction should have good consequences, of course. So we want to believe this finding. But then if you take a look at the main tests, and here they're actually nicely plotted in this table. You see that for experiment 1, the red box is around the main finding. For experiment 1, there's a p-value of 0.01. For study 2, the significance level is 0.08. So p-value is a bit too high, but okay, this is science publication. Not everything has to be significant. It's fine. Then we see 0.04, 0.04, 0.04. So there are 3 studies that are just borderline significant. If you do tests on this, and there's a test called p-curve analysis, which basically tests the distribution of p-values, then you get this sort of pattern that looks a little bit weird. You have a lot of these high p-values, you don't have a lot of these low p-values. This is reason for concern. So we can now recognize this sort of in the literature and say, well, maybe we shouldn't believe this finding yet, because it looks a little bit too good to be true. You can also look at a whole bunch of studies meta-analytically. And this is another example where people reanalyzed the meta-analysis. So there was a huge amount of studies that showed, okay, general effect seems to be true. In this case, the field was ego depletion. And ego depletion research is sort of looking at people's decline in cognitive cognitive resources to control their own behavior. So at this moment, you've been listening to me talk about 40 minutes, and now you're sort of thinking, oh, I'm getting a little bit depleted, basically, right? My cognitive resources are running low. I've tried to pay attention for a long time. And what they do in these studies is, for example, go around with people who are actually, for example, trying to diet. They give them the choice, do you want to have a nice fresh brownie, which is very unhealthy, or do you want to control your behavior and actually have healthy vegetables or radishes? And then if people are depleted, they're supposed to be more likely to choose the unhealthy food because they can't control themselves. They've lost the ability to control their own behavior. However, if you look at all these dots in a meta-analytic tests, here we see a funnel plot. So that's the triangle. And if a study falls within the triangle, it's not statistically significant. Again, this is just a statistical property, and visualizing it in this way makes kind of sense to quickly see this. If dots fall just outside of the circle or of the triangle, then they are statistically significant. And if you look at this, you actually see sort of a peculiar concentration of dots just outside of this triangle. Doesn't really look like it should look if you would randomly simulate data. And then you can apply statistical techniques to estimate, well, if this research field was not so biased, what would be the average effect size? And you can say, well, it looks like it might be actually kind of slow or kind of close to zero. And in this case, there have now actually been two very large-scale replication projects that have tried to find support for ego depletion. And both of these has shown effects that are basically zero. So it turns out that, yeah, if we looked at this statistically, we could at least see that something was wrong. And large follow-up tests so far seem to indicate that indeed there might not even be an effect, even though the meta-analysis showed maybe almost 200 studies that showed effects, seemingly showing that something was going on. So what's the third way that we can solve these problems? And I think this is the most promising one. That's trying to collaborate, right? Making sure that we end up in this more collaborative corner of the social dilemma. And there have been some nice ways to try to do this. There are some projects that come out of this new Society for the Improvement of Psychological Science that has a yearly conference where people get together. And it's a little bit like the hackathon that you're going through today. So people get together and it's a conference, but instead of just listening to talks the entire day, people might talk to each other, point out some problems, and then they break up in small groups and try to figure out how can we solve these problems. And one of the things that they've done that comes out of this is known as now the Psychological Science Accelerator, PSA, which is basically a large-scale collaboration. People got together and they said, well, how can we improve psychological science? Well, one way is to improve collaboration. So they invited huge amount of labs to contribute to work together and figure out stuff by collectively examining some sort of question. And now I mean, this is all starting up. They're running their first big experiment where everybody collects data all over the world. I think now they have sort of up to 300 individual labs from all across the world, so they can do very good representative research, and everybody will just pool these resources. So this is, of course, a very exciting way to do research, right? On a massively collaborative scale. Instead of tiny labs trying to show something, everybody just sort of pools their resources and figures out what's likely to be true. So some other things that we've been working on to try to improve things is teaching people how to improve, right? I mean, sort of also things that you're doing, where people show you something. There are tutorials where we train people how to do certain things that they didn't know before. And again, this is necessary because it might seem that things like the internet have been around for a long time, but it's actually not true. So, I mean, I'm already too old for most of the stuff that you're working on, but people slightly above, who've been in science 10 or 20 years longer, they also have to learn all these new things that are being developed. So one of the things that in psychology is happening is that actually we've recognized that this is so important that there's now a specific journal that's called Advances in Methods and Practices in Psychological Science, which publishes articles specifically about, well, as the title says, advances in methods and practices in psychological science. So they sort of realize the need of a journal that will communicate in an accessible way whatever kind of new improvements are going on. So if you're working on a specific field and you say, hey, this kind of statistical technique is pretty cool, or this kind of way of preparing or sharing data is something that people should know about, yeah, you can now write an article that's accessible and understandable for example, a PhD student, and you can submit it in this journal. So it's kind of showing the appreciation or the importance of this kind of information, right? We realize that we need to train people to do a better job, and we actually have this journal for it. So if you didn't get any of my comments about statistics and you would like to figure them out, you can take a look at, for example, my Coursera MOOC, which is free. So, I mean, you can just enroll, don't have to pay anything, don't make any money, that's fine. But I think that this is also a nice sort of way of using the internet to reach way more people than before. And statistics is not always intuitive. Many of these new things are not really taught. They're not part of the curriculum. So there's a lot of things that people should know, but they're not really trained in. So these kind of courses, and you see more and more of these kind of resources online, can be really great. The second thing that we realize is more important than we thought is organizing what we actually already know. So one of the things that I think is pretty cool initiative here is something that's called Curate Science. So now we think sometimes research might not be very reliable. People might try to perform a replication study, but then it's actually very difficult to figure out if it is reliable or not by finding these replication studies. We have a very limited way of organizing the scientific literature. You have to really search through everything and find things yourself. The goal of Curate Science is to provide you with a very nice overview. You can go to the website, you can look up specific studies, and they're still starting up, so it's not like the entire literature is available, but there are kind of big replication projects that are all curated, where you can just click on a link to the data, to the pre-registration, or to the materials, if these are available. They show the effect sizes of individual studies and of replication studies, so you sort of can get an immediate overview of everything that's going on within a specific research line. And this kind of curating work is pretty cool and important, I think. Because, yeah, now it's just very difficult to keep keep a feel of what is happening with a specific finding. Another nice initiative where people can share data that are not statistically significant, so they might not feel like publishing it, but you still want to communicate that you have a finding in your file drawer, then you can upload it to this website, Psych File Drawer. So if you have stuff that didn't work out, you didn't know what to do with it in the past because you didn't think that a scientific journal would be interested in publishing it, you can now share it online, so at least it's findable for people who want to do a meta-analysis. And again, something that the internet makes a lot easier than before. Another thing that we realize is important is that we have to make it easy for people to actually build on the work of other people. And sometimes that means replicating previous research. And in the case that we want to actually stimulate people to do this, so again, we have this social dilemma, right? Why would I spend time replicating your work when you're doing all the novel, interesting things? I mean, I'm not rewarded to check your results. It might be more sensible for me to do novel things as well. So this is problematic. So one thing that is now being done is that people are explicitly funding research on replications. So they are now, for example, the Dutch Science Funder is one of the first to make 3 million euros available exclusively for replication studies. So if you want to build on the work of someone else, to replicate it as close as possible in a huge sample, a large sample, then you can request a grant for this and actually have money to do this kind of research. Because if we think it's important to do, we should also reward people to do it. And finally, there's a lot of work on reproducibility, which is, yeah, getting more and more important. It's also getting easier and easier to do with, again, things like, you know, basically technological developments make this easier than it was before. And I know that some of the workshops that are going on at Brainhack Zurich are also around improving reproducibility. I just wanted to show one thing that I kind of like, which I don't know if you heard about it, but it's kind of nice. I know that you'll get some, there's some workshops going on where people have to install Docker. And I think neuroscience community is pretty far ahead with the use of Docker and those kind of technical solutions. I find that, yeah, tricky, sort of challenging, but I do want to make sure that someone else can completely reproduce my data analysis when I do it. And CodeOcean is a website that is sort of Docker, but then online. So I can just go online, I can create a container. This container can be, for example, the R interface. I can upload my data. I can upload code. And then within this online environment, people can basically press a button, rerun my analysis. If they want to change something, just go into the code, make some changes, and rerun the analysis and see the results, the outcome of the analysis. All right. So I think there's still kind of enough left to improve. But I also think that it's kind of exciting to see all this stuff happening. So I don't want to sound too old, but I think that a lot of these things that are going on since maybe 5 years or so are really, really changing the way that we work in the field. And it's extremely exciting to see this. Sometimes you might think, why haven't we already introduced this? Why isn't everybody doing this? But then, yeah, you have to sort of think of science not as a sort of, you know, a speedboat that can just go everywhere. Science is sort of a huge container ship, basically. You know, it's drifting somewhere. And if you want to steer it in a new direction, you know, you move the steering wheel and then 15 minutes later, it will slowly move in that direction. That's sort of how science goes. But then if you look at many of the recent developments that are going on, it's actually changing remarkably quickly. And introducing certain suggestions or new things can actually be picked up by a lot of people in a surprisingly small amount of time. All right, that's all I wanted to say. Thanks for listening to me. Thanks for your attention.
Thank you. Are there any questions? Can you hear me?
I can hear you, yeah.
Let me come closer. Well, I said you can't hear me. Okay, well, I'm going to stop here. Yeah, I was actually quite a bit shocked by your presentation. I mean, you brought it to a really nice end, and then a lot of the technologies about which you talked at the end. But I'm really quite surprised to be here at an event where we learn to be like empowered and free and hack and modify code so that it does the work in which we want to get it done. And then to hear a presentation which tells us that we need more rules, that we need more bureaucracy, and that we might need even more punishment. That sounds like the prelude to the scientific apocalypse for me. Especially regarding pre-registration. I mean, like a lot of people, I started my PhD thesis by trying to reproduce somebody else's work because you can never be sure that it works. And in my case, luckily it did. But the entire idea with pre-registration is the problem which you have with like p-hacking and so on. It's not the problem with how science is done, right? It's the problem with the fact that statistics cannot accurately describe exploratory science. A scientific project doesn't start with a question, well, can I refute hypothesis? No. A scientific project generally starts with a question, what would I find if I did X? Because what motivates curiosity, and this is how we work. And if I look at my own project, it was always like picking out of the things that work and patching, and picking out of the things that work and patching, simply because you develop technology, you develop new methods. This might be less pronounced in psychology, but I'm sure there's a bit of that going on as well. So the way I see it is pre-registration might be really well suited for a couple of clinical studies, perhaps, where you have a pretty well-defined hypothesis, and where you maybe even have a specific paper which you're trying to reproduce. But for most research, I think it's simply unapplicable, and recommending it so highly, I think, is dangerous because it will force people to try to lie and construct like loose hypotheses even more in order to get this like seal of approval. Motivating them to be honest and to just say, okay, well, this is what I did. I had like maybe 2 hypotheses which were super loose, but the main thing I wanted to see is what kind of effects could we observe, and these are the significance values which I got out. Of course, they're not entirely credible, so this will only become a real study once it's been reproduced. And then something to reproduce it might be looking to register. But I think for most creative research, it's a catastrophe. Don't you agree?
So just to get this clear, so at the end you said, so I publish something and then someone else can replicate it, right? If someone else replicates, we don't know whether these p-values are correct, but someone else can replicate it.
It's like an indicator for a power analysis, yes.
Yes, so that means that you would not replicate your own finding.
I might at a later time point, yes.
But you would publish it without replicating it first.
Yes, exactly. That's how exploration functions. Yeah. I need to communicate it as fast as possible, right? There's no use sitting on the work I've done.
Yeah, so the question is how you can actually make sure that you're not fooling yourself, right? I think that what we've seen in the past is that whenever people publish exploratory findings, they have a tendency to fool themselves. And I think that's, well, there's a nice quote by Richard Feynman that, you know, you don't want to, scientists shouldn't fool themselves, and you are the easiest person to fool, basically, right? You can fool yourself quite easily. So there are two ways to prevent this. And one is pre-registration, because you have a good prediction and you want to convince me that you actually were able to show something. Now, that is indeed not the case for exploratory or purely descriptive research, where you just do something and you say, well, this is what we've done. And exploratory research is fine if it is presented as such. And this is another case of not fooling yourself. So what we don't want to do is have somebody who does purely exploratory research and then says, look, I have discovered this, because that's very difficult from exploratory research. What you actually see is that someone like Chris Chambers, who's promoting these registered reports, recently also started the first exploratory reports. The goal is not to chain people in one specific way of working. It is to make what you are doing extremely transparent. So transparent that you cannot fool yourself and you cannot fool other people. So in that sense, if the pre-registered approach doesn't fit your way of working, that's totally fine. But then you can go for these exploratory reports and say, look, I'm not even calculating statistics here, because I'm just looking at my data in so many ways that statistics immediately lose their meaning, right? Because this is true if you don't really limit the way that you analyze your data, you just explore it. Well, you can do, of course, certain things, but it's very difficult to confirm that the result is correct. There are many other ways to solve this. So you might not want to do a pre-registration, but maybe you have enough data so that you can do a split half analysis. This is also a lovely solution to this problem. You can go crazy on half of your data, and half of the data you just store somewhere. Maybe you don't even have access to it yet. You explore everything, and then the moment that you want to say, I think I know something, then you can demonstrate this in the other half of the data. Again, the main goal here is just to say that whenever you say, I know something, you're not fooling yourself, but you actually really know something. And I think that what we've seen is just people are not very good at distinguishing this themselves without some sort of formal support around this. So if we leave this completely up to people, it becomes extremely messy. Now, that doesn't mean that you're not allowed to explore anything. It's just that when you are exploring, you really know that you are exploring. And I think if you see it as sort of a restrictive process, that's not really correct. But if you want to predict something, that is a very restrictive thing. You say, look, this is going to happen in the future. Trust me. And why should I trust you? Well, because you demonstrate that actually this is going to happen. Now, you don't have to do that kind of research. You can also say, my role in science is to explore. I just play around with stuff and I let other people figure out whether it actually works or not by replicating my work. Or, yeah, I might try to replicate my work in the future. Now, statistics is limited in any way. Replication is always important. Whenever anything you do is based on statistical processes, someone needs to replicate your work. Now, it might be you. You might find it important enough not to say anything that might be wrong because you first replicate your own research. Or you might be, well, I'll leave it up to someone else. And then luckily now we have actually replication grants to reward other people to actually test your work, because otherwise everybody's going to do the exploratory kind of novel thing, right? So I think that's sort of how it works. We see in past that letting people have complete freedom has the unfortunate consequence that they fool themselves. Maybe complete freedom, lack of transparency might be a better word. So I think people are completely free to do what they do. And as an example, there's often talk about something that's called questionable research practices. So this kind of cooking or p-hacking is very often called a questionable research practice. One of my favorite papers on this says, there are no questionable research practices. There are only questionable reporting practices. And I'm totally fine if you publish a paper where you say, hey, I explored my data in a lot of different ways. And then I removed from my sample everybody who is left-handed, because these left-handed people are weird. And I also only looked at the data after 200 seconds of doing this. And then I also did this. And I also transformed the data to a logarithmic function, and then I found this. Sure, perfect. Just write it down like you did it, be transparent, and then I know what I'm looking at. So it's sort of tricky to just let you make these decisions without this transparency. So would you have like another suggestion of how I can see what you've been exploring? Do you have a sort of ultimate transparency solution for that? Because I would be interested. I'm fine not pre-registering anything, but then how do we get this level of transparency where I can see, I don't think you're fooling yourself or fooling me? Do you have a solution for that? Something else?
I guess if you're looking for an ultimate solution for anything, you're going to end up with these really weird systems which try to force people to do things. But my solution would be not an ultimate one, but I think one which preserves freedom a lot better, which is you judge the credibility of the paper in light of its transparency. The way I read a paper is if I can't reproduce it, then I don't really believe it. And I think that's a correct position to have. Simply because otherwise you relegate credibility to a sort of like priestly veneer of scientists. Oh my God, this person has like pre-registered his study. He might be able to see the future. Because that's what you reward when you say that, wait a second, that's what you reward when you specifically say that hypothesis testing is more important than exploration. You don't reward rigorous exploration and rigorous work, but you reward the capability to see the future, which is ludicrous, right, as you've previously shown in your example. I'd rather reward the capability to do rigorous research and to document it, which is best reflected in the fact that the paper contains the data and the software.
Well, I mean, I agree that that's always a sort of minimal requirement, that data or a paper contains access to the data. But I think that the conclusions that are drawn, and it really depends on how it's written up, right? I mean, I can see some really nice exploratory papers. I mean, there are not a lot of good examples because scientific publications, and especially the more, let's say, prestigious journals, don't really reward this kind of level of transparency at the moment, at least in my experience. They more reward a nice story. And really rigorous exploration is always extremely sort of messy, right? It would require a huge write-up of whatever actually happened. Very often what we write up is the end result of rigorous exploration, as if we actually predicted that we were going to do this all along. Or we create some sort of story that we think is plausible after we have explored a lot of things. At least in my field, that's very common. And that leads to these problems that if someone else then tries to build on it, that doesn't work for most of the findings. So in psychology, we had this big reproducibility project, and we can just see that the level of reproducibility is not as high. And then I don't mean, well, I mean replicability, actually. So it doesn't replicate. It reproduces fine, because if you looked at your data in 500 ways and then you store the data analysis and the data, I can, of course, reproduce whatever you found. But if I collect a new sample, then that doesn't work. So it really depends on how big the problem is in that sense. And like if there's a problem with replicability, then you might want to make sure that we have this sort of level of transparency. And that's not limited to the data. We need something more, because all statistics have the assumption that, well, you had a plan beforehand. There was some sort of sampling plan that was fixed. So it's fine to explore, but then just do not report statistics, for example. Right? That would be perfectly fine. Or just descriptive statistics, but not a p-value, nowhere. Because if you explore, then a p-value is immediately meaningless. Right? Do you agree on that, at least? Yeah. So you can have descriptive statistics and just say, look at these patterns. They might be interesting. And that can be a very interesting paper. On the other hand, sometimes you want to say, look, yeah, we made a prediction. And I'm not saying that that research should be more important. I think also that's why, actually, if anything, I think exploration will get higher credibility. Because now we rarely see real exploration in papers. We really see this more coming up with a story after the fact. So true exploration, hopefully, will be liberated a little bit more with the introduction of pre-registration, because this is very strict, but then you can also see the other side. So I think really, I mean, I'm fine if you say, no, I don't have hypothesis. I don't think it's important to test hypothesis. And that's perfectly fine. Then don't do it. just saying that if you do it, then do it in the right way. And if you don't do it in the right way, right? So in practice, I think that, yeah, the concerns about this, well, I think it's very often seen as sort of restrictive. There's a nice paper that will come out in the future that pre-registration is actually very liberating, because you can just be perfectly clear about what you've done. It's sort of an opinion piece, and I wasn't actually convinced in the beginning when I read it, but I am now. So I think that the view that it's very restrictive should probably be transformed into a view it is extremely transparent what has happened. Now, it could be that there are negative consequences, that we will see pre-registered research as more reliable. And I know that people are already examining this, so already testing hypotheses. And if this is not justified, then we might want to correct that belief, right? So science is always improving. Now we have done some stuff. I think there are some reasonable improvements. And I think having pre-registration, at least for certain tests, is actually a benefit. But there will also be things that go wrong. And maybe your concerns are correct, and we have to correct them in the future. And it would be kind of silly to think that now 2018 is the year when we've got it all figured out and everything is fine. And there's no longer any kind of negative consequence of the way we've got science organized. So if you have a big concern about the position of exploration in research, you think that there are negative consequences about it, then it's a perfect thing to spend some attention on and try to make sure that, I don't know, you create exploratory reports, or you find a way that people can transparently report exploration without fooling themselves, and you explain people how to do this. But I don't see that very often, so I think there's actually a lot of room for improvement there. Do we? Can we meet somewhere halfway on this?
I guess that answers my question.
All right. Yeah. But don't think that we're there, right? I think that some of these initiatives solve specific problems, and some of them might also create problems. And we should be very open for them and think about how we can prevent that.
Any other questions?
Do you have an opinion about base factor analysis?
Sure. I think I just saw some people. So I do a little bit of statistics, even though I'm not a statistician, and I was involved in a nice project where the same data set was analyzed in 4 different ways by 4 different field teams, and they all had different approaches. Some used Bayes vectors. I typically use frequentist statistics. I'm actually one of the few people who think that p-values, when used right, have a specific function of error control, which can be useful. There were more estimation-based approaches, both frequentist and Bayesian. What was interesting in this project is that all results, or all approaches, basically gave the same final interpretation. Not saying that there are not philosophical differences, but actually in the work by Jeffries, who's developed Bayes vectors 1935, in response to Fisher, he says, well, I've looked at many of the issues that you've looked at, many of the same data sets. I've analyzed them in my way, Bayes vectors, and I very often reach the same conclusion. I'm a big fan of complementary approaches. So I would say there's very rarely a reason to limit yourself to one statistical approach. There are almost always benefits of looking at the same data from multiple ways, and then if these all line up, which in many cases they should, then that's a good sign. Whenever they disagree, it's probably a good lesson, right? And it probably means you want to be a bit careful about the data analysis. This is also what Jeffrey says. So we would only disagree in situations where we should be very doubtful about the data anyway. So in general, I would say it's useful to know about them. I do teach always about Bayesian statistics and Bayes vectors. Yeah, and I would like to see people use more. That's was a bit of my goal in 2018. So I think that there's a little bit of a polarity between these approaches, and people have a lot of discussions about which is good and which isn't good. I think, you know, it's really not so much of it shouldn't be so much of an issue. And it shouldn't be something that researchers think I have to have a principled position on where I only choose a side. No, just do both. And there's really no problem. And we wrote another paper about analyzing null results through equivalence tests, which are frequentist, and Bayes vectors, together with Zoltan Dinas, who I like a lot and does a lot of work on Bayes vectors. And that was also a little bit of a goal to show you can just do the same thing together and it's fine. Is that an answer?
Yeah, thank you. I was actually also referring to something.
Aha. Okay. Yeah. Good.
What I really liked about his approach was that he really thought about effect sizes before starting the analysis. And even though he would find an effect that supports his theory, he would still reject his hypothesis when the effect size is just too small.
Yeah. Yeah, and I love that about the Bayesian approach in general, although, of course, actually in frequentist approaches, name and Pearson statistics, you have to think about the alternative hypothesis just as much, for example, to calculate power, or at least a minimal level of power for an effect size you find interesting. And I think this is something that we can improve in as well, because if you think about what you actually predict, and no, hypothesis testing is a little bit limited in the sense that the alternative is anything else. And anything else is a lot of stuff. It's difficult to falsify a prediction that says, well, my alternative is anything else. I agree with you that it's very nice to say, I expect an effect in this range, and otherwise I don't believe it. I have a blog, and I recently blogged about a finding that's pretty well known, which is called the hungry judges effect. And it's maybe you've heard about it in the popular media somewhere, but it's an effect that judges, when they have to choose whether someone gets parole or not, just before lunch, they become much harsher, and they actually are less likely to give someone parole just before lunch. And I looked at this data, and this effect size is huge, way too big to be plausible, which probably means that there might be some effect, but it's probably not due to how hungry you are, maybe based on how they order the cases or something else, but there's something else going on. This is, I think, a good example of where an effect size is so large, even though it's hugely significant, it's too large to actually be support for your hypothesis. So I think this is an important thing to keep in mind, and it would improve science if people do this a little bit more, whether it's based on Bayesian statistics or any other kind of approach. Yeah.
Thank you.
Any other questions? Well, a very quick one. You talk about these replication funds. Are they available just in the field of statistics or also for other hard science such as physics?
Sorry, can you repeat the beginning?
These replication funds.
Okay. So at the moment, as far as I understand, they exist in the US has them, and the Netherlands has them. In the Netherlands, they are specifically for fields that rely on statistics in social and medical sciences. So not for physics. I'm not sure. I think the reward structures might be a bit similar. On the other hand, some fields have a much stronger tradition of replication already, where replication is necessary to build on the work of other people. And some fields have this a little bit less. So in psychology and some social sciences, this tendency to start out with a replication, which somebody mentioned was common, at least in your lines of research. This is not so strong in other fields, and then publishing these results was also much more difficult if there was a no result. And I think in physics, this is a little bit easier. So as far as I know, currently, these replication grants are only available for psychology and social sciences. Now, I have to say that I was one of the people who actually recommended our Dutch science funder to introduce these. They looked around where the need was greatest, and they apparently identified, well, not physics as a field that really needs it. Do you think it is important for these fields to have them?
Absolutely. I did it myself, and I come to so many wrong papers in my career. And the problem is that when the papers are published, they are not typically double-checked by someone else. And there are so many papers that are wrong out there.
Yeah, it's interesting to hear, I would say. So when I approached the science funder about these replication grants, I was, I think, first year, second year postdoc, and I didn't have any kind of prestige. I'm not sure if I have it now or if it matters. But the thing is, if you think that this is important, go ahead. I mean, what does an email cost? Contact the science funder and say, hey, I think this is a good idea. Let's have a very small percentage of our funding dedicated to replication studies. It sounds to me like a very reasonable thing. Science funders have two roles. The first is to generate novel research. very often the second goal is to make sure that they generate reliable research. Well, if we want to have reliability, we need replications, so they should also be funded. That was sort of my, in 20 seconds, the argument I made to the science funder. And I think that the Swiss science funder is very interested in these kind of issues. I've spoken there a couple of years ago about reproducibility and replication. So give it a try. Who knows? Maybe you'll manage to convince them.
Maybe. Hopefully. Thank you.
So Daniel, do you have any practical advice for PhD students about how they can convince their PIs that it's worth spending time and effort doing open, transparent research?
That's a good question, and one that very often comes up. So you're working very hard on thinking about best practices, and then you have to convince other people, maybe in your department, to do this. One of the things that when I look around, seem to work very well. So now you're all getting together, right? Sort of on an ad hoc basis. There are also groups or people that at a university get together as sort of let's say an open science committee. And these open science committees will do a lot of things. So they will, for example, help people out in figuring out how they should share data or where they should share data, or they generate informed consent forms that actually allow you to share your data, or they would, I don't know, any other type of best practice that's useful in a specific department or in a faculty. The Open Science Committee gets together and gives basically recommendations. And the nice thing about an Open Science Committee is that you are not just a single person trying to say, hey, it would be good if we do this, but now you are an official entity within the university. You are the Open Science Committee. So you can say to your supervisor, instead of saying, I think we should share our data, you can say, the Open Science Committee, which might still be you and your fellow colleague, but okay, the Open Science Committee says that we should share, recommends that we should share our data. And that's actually a feasible way to get started. Many of the tasks that need to be done, because we are moving to a system where, well, many journals now require that people deposit their data, right? This is a move that's not, it's going in one way. It's not going to go back. So, so it's good to have people to actually figure out what good practices are and share them with their colleagues. So that's one recommendation. And the other is there's actually many good selfish reasons to do this. I'm not sure if that's necessary, but if you think that just doing the right thing is not enough to convince someone, then even journals like Science, maybe already or in the near future, require data sharing with publication. There are now the top guidelines, the transparency and openness principles, I think, the guidelines that journals subscribe to. They're at certain levels, but we can probably expect that these levels will increase, and certain journals adhere to these guidelines in certain levels. And data sharing is actually a requirement for many journals now. So if you want to publish, you might as well start preparing. If you want to publish in 1 year or 2 years in a nice journal, then now you might already want to prepare in having this sort of open and and reproducible analysis pipeline, for example. So there's a bit of a self-interest, and there's a bit of a recommendation to make these recommendations collectively by getting some people together that care about this and getting a slightly more official status. I've seen people do that, and that works pretty well.
Okay. Any other questions? Well, Daniel, thanks so much for connecting with us.
Yes, thanks.
Thanks for the great talk. And
all right.
A nice evening.
All right. Have a great rest of the conference, people.
Thanks so much. Bye-bye.
Bye.